In part 1, we've seen how to find the lowest common ancestor of two nodes in a binary search tree using a recursive solution. So remember, the lowest common ancestor is the last node that is in common in the paths to the two nodes. And what we did, we determined that in a binary search tree, all we have to do is move to the left if both the nodes have a value that is smaller than the current node, and move to the right if they both have a value that is larger than the value of the current node. Otherwise, this is where the paths start to diverge, so this node is the last node in common in the two paths, so we return it. Let's quickly see this with an example. Here we have the same binary search tree we've seen before. And let's say we wanted to find the lowest common ancestor of 3 and 5. We would start at root, and then we check, are both 3 and 5 smaller than root? So 6, yes they are smaller. So we would move to the left by calling the function recursively with the left child. Then we would check, are 3 and 5 smaller than 2? No, they are not. Are they both larger than 2? Yes, they are. So we would move to the right by again calling the function recursively with the right child of 2. Then we would check again, are both 3 and 5 smaller than 4? No, they are not. Are they both larger than 4? No, they are not. So this is where the paths start to diverge, and this is the last node in common in the two paths, so we would return it. So 4 indeed is the lowest common ancestor. Let's see how to implement this process iteratively. So we again have a function called LCA, which takes the root node, and then it takes the nodes n1 and n2, of which we want to find the lowest common ancestor. And we return the lowest common ancestor. We begin by setting current to the root node. Then we would enter a while loop from which we exit within the body. So the first thing we'll want to do is to save the value of current into a shorter variable, so val, so that we don't have to write per value everywhere. So what we want to do is to check if both the nodes have a value that is smaller than the value of the current node, then we move to the left. Otherwise, if they both have a value that is larger than the current value, then we move to the right. Otherwise, this is where the two paths start to diverge. So current is the last node in common in the two paths, so we just return it. And that's the whole function. Again, remember, we don't need to worry about root being null because we are assuming that the two nodes are in the tree. So when we call the function initially, root cannot be null. And then when we move to the left or to the right, we are sure that both nodes are either on the left or on the right. So current cannot become null. Let's verify that this function works by running through some examples. Let's say we want to find the lowest common ancestor of 3 and 5, so n1 would be 3 and n2 would be 5. So we call our function, passing in the root of the tree 6, and then n1 3 and n2 5. First thing we do, we initialize current to the value of root, so 6. Then we enter our while loop, set value to the current value. We do this just not to write current value everywhere. So we check, are both n1 and n2 values smaller than value? So 3 and 5 are both smaller than 6, so this is true. So we set current to current left. The left of 6 is 2, so current becomes 2. Then we go back to the beginning of the loop. we check, are they both smaller than the current value? So n1 is 3, n2 is 5. They are not smaller than 2. So we check, are they both greater? So 3 and 5 are greater than 2, so this is true. So we set current to current right. The right of 2 is 4. So current is set to 4. We go back to the beginning of the loop. We check, are both n1 and n2 smaller? This time they are not both smaller. Are they both larger? They are not both larger. So we hit the else, and we would return current, which is 4, which indeed is the lowest common ancestor of 3 and 5. Let's verify this with another example. Let's say we want to find the lowest common ancestor of 2 and 5. So we begin by calling our function with root 6 and 1, 2, and n2, 5. We initialize current to root 6. We enter our loop. We check, are both n1 and n2 smaller than 6? Yes, they are. We set current to current left. The left of 6 is 2. We go back to the beginning of the loop. We check, are they both smaller than 2? They are not. Are they both larger than 2? So 5 is larger, but 2 is not larger. So this is false. So we hit the else and return current. So 2 is indeed the lowest common ancestor of 2 and 5. Remember, a node is considered to be a descendant of itself. Let's analyze the time complexity of this function. Because every iteration of the while loop, we either move to the left or to the right, that is, we go one level deeper in the tree. In the worst case, the two nodes are at the very bottom of the tree. So the loop will run h times, where h is the height of the tree. And because every iteration we do a constant amount of work, this means that the work associated with the while loop will be O of h. And then outside the while loop we do just some constant amount of work. So the time complexity of this function is O of h. This again is log n in case our tree is balanced. Let's analyze the space complexity. The space complexity is O of 1 because our function uses a constant amount of space. You can find the link to the code in the description below. If you have any questions or comments, leave them in the comment section below.